Welcome to The Deep Dive, the show where we cut through the noise and get straight to the most fascinating insights from cutting-edge research. Today, we're plunging into a truly groundbreaking area. AI not just, summarizing information, but actually performing deep, multifaceted research. We're talking about deep research, or DR agents. So what exactly is a deep research agent? Let's try and unpack that.
Well, imagine an AI system. It's powered by these large language models, LLMs, right? And it's specifically designed to tackle really complex informational tasks.
Okay, complex tasks.
Yeah, think of it like an AI that can reason dynamically, plan adaptively, retrieve data from all over the place, the internet databases, whatever, over multiple steps. And it uses a whole toolkit of external instruments, and then it generates this comprehensive analytical report.
Wow. So our mission today, our goal is really to give you a shortcut, a clear understanding of this rapidly evolving field. We want to unpack what these DR agents are, how they actually work, and, what their future might hold for you.
Exactly. And what's truly, I think, transformative about them
Yes, sir.
is how they stand apart from earlier systems, like traditional retrieval augmented generation, RA,
Yeah.
or even just conventional tool use systems.
Right. RA is more about fetching facts, isn't it?
Pretty much. These DR agents, they offer significantly greater autonomy. There's continuous deep reasoning, dynamic task planning, adaptive real-time interaction. It's like moving from a very sophisticated librarian.
To a full-fledged independent researcher. Yeah, I get that. And to give you a mental picture, our sources describe this general workflow that sounds, frankly, incredible.
It is quite impressive.
So you, the user, you ask a complex question. What happens next?
Okay, so the agent kicks into action. It plans its approach. It starts using various tools,
On a tool.
retrieving information, right, from offline databases, the live web, performing data analytics. It can even write and execute code or generate multimodal content like images alongside text,
All from one question.
all driving towards answering that initial complex query. And ultimately, it produces this really comprehensive, structured report.
It sounds like a complete end-to-end research powerhouse, taking on stuff that used to need whole teams.
That's the idea, yeah.
All right, let's dive into the core mechanics then. How do these agents actually think? How do they process information at such a, deep level?
It really starts with foundational advancements in how these LLMs reason. A key technique you hear about is chain of thought prompting, or COE.
Chain of thought, right.
Yeah. It basically guides the AI to articulate its intermediate logical steps. It sort of forces it to show its work, breaking down complex problems into smaller, manageable stages.
Which helps with accuracy, I imagine.
Hugely. It makes the AI's reasoning more transparent, and it definitely boosts accuracy. We also see other clever techniques, things like positional interpolation or sparse attention, that effectively extend the memory, the context window of these LLMs.
So they can handle more information at once.
Exactly. Well, much more in their immediate context.
Yeah.
And if we connect this back, earlier our RAG approaches were great for factual accuracy, helping with AI hallucinations and all that.
Sure.
But they often fell short on sustained reasoning and that dynamic adaptation we talked about. Agentic R-Grade tried to add some reasoning layers, but it was still often limited, relying on pre-existing or maybe periodically updated knowledge bases.
So it wasn't truly real time.
Not in the same way. The core motivation for DR agents was really to break free from those constraints, to let the AI actively integrate real-time external information, enabling truly dynamic and adaptive research.
So it's not just about retrieving existing facts from a database somewhere. It's about actively reasoning through the information it finds and adapting its strategy as it goes.
Precisely. It's about ongoing, iterative problem solving. The agent refines its understanding, it refines its approach with each new piece of information it uncovers. And that unlocks research questions that were just, impossible for automated systems before.
That sounds incredibly powerful. But okay, with this level of autonomy, how do they connect? How do these agents talk to external services or maybe even talk to each other to collaborate on really big challenges?
Yeah, that's a great question. And this is where two really pivotal concepts come into play. There's the Model Context Protocol, or MCP, and Agent A2A protocols.
MECP and A2A.
Okay, so MCP was developed by Anthropic.
Right.
Think of it as a kind of unified communication layer, a universal translator, maybe.
Right.
It lets LLM-based agents securely and consistently interact with all sorts of external services and data sources using standardized interfaces. This helps solve those common headaches, like dealing with inconsistent APIs or siloed data, makes tool access much more efficient, more reliable.
Got it. Standardizing the connections outwards.
In A2A,
A2A is more about the agents talking to each other. This came from Google. It facilitates decentralized multi-agent collaboration.
so different AIs working together. Exactly. Imagine different agents, maybe even from different companies, built on different models.
Yeah.
They can discover each other, they can delegate specific responsibilities, manage complex tasks together through structured, task-oriented dialogues.
Okay. So they complement each other then. MCP handles the tools, A2A handles the teamwork.
You've got it. MCP provides that standardized interface for tools and external data. A2A orchestrates the collaborative interactions between the agents. Put them together, and you get this modular, scalable foundation for really interoperable AI ecosystems. It significantly expands what these systems can achieve when they work together.
Makes sense. Now, these agents, they obviously need to see the web, right? To gather all this information.
Oh, yeah.
How exactly do they do that? Are there different ways?
Yeah, there are basically two main ways they integrate with search engines and the web more broadly. First, you have API-based search engines.
Okay, using the official connections.
Right. These are super fast, very efficient, especially when you're dealing with structured data. Think of an agent directly querying, say, the Google Search API, or a specific scientific database API, like RSearch. Gemini DR from Google does this, using Google Search and RSearch APIs. Grok Deep Search from xAI maintains a continuous index using news feeds and the Wikipedia API.
What's the downside?
The main limitation is accessing dynamic content stuff that changes a lot, or content that's behind a login screen, or maybe information buried deep within a website structure. APIs don't always get you there. So the second type is browser-based search engines. And this is where it gets really clever.
Oh, so?
These agents actually simulate human-like interactions with web pages.
Like using a real browser.
Essentially, yes, often a headless one running in the background. It gives them dynamic, flexible access to all sorts of unstructured content, multimodal stuff too. Our sources mentioned Manus AI's browsing agent actually operating a sandbox Chromium instance that's the engine behind Chrome.
So it can click things, scroll.
Exactly. It can programmatically open tabs, click links, scroll down pages, fill out forms, even execute JavaScript to reveal content that isn't immediately visible. It's very likely that major players like OpenAI, DR, and Grok Deep Search use similar sophisticated browser automation frameworks.
Okay, so if the browser method is so flexible, why use APIs at all? Why not just use the browser approach for everything?
That's a good point. But it comes down to trade-offs, right? APIs are generally faster and more efficient for structured data retrieval. Browsing can be slower, more resource-intensive. So the optimal solution, what we're seeing emerge, often involves hybrid architectures. They combine the speed and efficiency of API-based methods with the sheer comprehensiveness and flexibility of browser-driven exploration. It's about getting the best of both worlds for different parts of the research task.
Okay, so they've gathered the information using APIs or browsers or both. What can they actually do with it then? What's in their toolkit beyond just retrieval?
The toolkit. Yeah, it's pretty sophisticated. It's primarily built around, let's say, three core types of modules. First, code interpreters.
Running code.
Allowing the agents to execute scripts, usually Python or maybe Java. They use this for all sorts of things, processing raw data, verifying algorithms, even running complex model simulations. Most advanced DR agents have this capability built right in. Second, we have data analytics modules. These are absolutely crucial for transforming all that raw retrieved data into actual structured insights.
Like summaries and charts.
Exactly. Agents can compute summary statistics, generate visualizations, conduct quantitative evaluations. For example, CoSearch agent can integrate SQL queries to analyze data and build reports. AutoGLM can directly analyze structured data it finds in tables on web pages. And third, there are multimodal processing and generation tools. This is becoming increasingly important.
Dealing with images, video, audio.
Precisely. Integrating and analyzing all these different data types, text, images, audio, video, within a single reasoning process. Now, this is complex stuff, computationally expensive.
So not all agents have this yet.
Right. It's typically found in the more mature commercial systems and some of the really advanced open source projects. Think Manus, O2EL, OpenAI, Gemini, Perplexity, Grok Deep Search. The big players often support this. And then there's something truly cutting edge, which our sources refer to as computer use. A good example is AutoGLM rumination.
Computer use, how's that different from browsing?
It goes beyond just simulated browsing in a sandbox.
Yeah.
It seamlessly integrates that advanced reasoning with authentic browser interactions,
Meaning?
meaning the agent can reliably access user-authenticated resources. Like it could actually log into a specific research database you have access to, say CNKI, or maybe even interact with platforms like WeChat official accounts if needed for the research.
Whoa, that's a significant step up in autonomy.
It really is. It dramatically elevates the agent's ability not just to acquire information, but to actually execute real-world tasks that require secure access or specific user permissions.
Okay, this is getting seriously complex. How do these systems actually organize all this? How do they structure their research? Is it like a fixed plan, a rigid set of steps, or is it more fluid?
That's a key distinction. The way they organize their research workflows generally falls into two main types: static and dynamic.
Static versus dynamic. Okay.
Static workflows are, as you said, more like that rigid recipe. They rely on manually predefined task pipelines. These are actually pretty good for scenarios that are very well understood, very predictable.
Like,
Maybe an AI scientist designed for a specific type of scientific discovery,
yeah.
or something like Agent Laboratory, which uses highly formalized research stages. The big limitation, though, is generalization. They don't adapt well to new or unexpected situations. Each unique task often needs its own specific pipeline build. In contrast, dynamic workflows are much more fluid, more adaptive. They support adaptive task planning.
Meaning the agent can change the plan midstream.
Exactly. The agents can dynamically reconfigure their task structures based on iterative feedback, based on the evolving context of the research. This adaptability is absolutely crucial for those complex, knowledge-intensive tasks that DR agents are designed for. It lets them pivot, lets them adapt in real time as new information comes in or the situation changes. And within these dynamic workflows, there are also different ways the underlying LLMs actually approach the planning part, especially how they figure out what the user really wants.
Different planning strategies.
Yeah, three main ones highlighted in the research. The planning-only approach is pretty common. It just generates the task plan directly from your initial prompt, no back and forth. Most DR agents, like Grok Deep Search, H2O, Manus, tend to use this. Then there's the intent-to-planning strategy. Here, the agent actively tries to clarify your intent first, asking you targeted questions before it even starts generating the plan. OpenAI DR is noted for using this approach.
So it understands the request properly first.
Right. And the third is kind of a hybrid: unified intent planning. It generates a preliminary plan based on your first prompt, but then it interactively engages with you, the user, to confirm or revise that plan. Gemini DR is a good example here, benefiting from that user guidance loop.
That raises an interesting point, doesn't it? How much interaction or guidance do we as users actually want in that planning process? Is it better to let it run or be more involved?
It's a critical design choice, absolutely,
Right.
and likely depends on the user and the specific task.
That is fascinating. Okay, so when a DR agent tackles one of these complex problems using a dynamic workflow, is it one super smart AI doing everything by itself, or is it more like a team of specialized AIs working together?
That's precisely the distinction between single-agent and multi-agent systems, especially within these dynamic workflows.
Right.
In dynamic single-agent systems, pretty much everything, the planning, the tool use, the execution, it all happens within one unified large language model. It streamlines the whole process into a single cognitive loop, if you like.
Exactly.
Systems like Agent R1 and Research work this way. The big advantage is you can potentially optimize the entire workflow end-to-end using reinforcement learning, leading to really smooth integration of reasoning and tool use.
But the downside.
It puts immense pressure on the capabilities of that single foundation model. And it might be less flexible for really complex tasks that could be broken down and done in parallel, which leads us to dynamic multi-agent systems. These leverage multiple, often specialized agents working collaboratively.
Like a team.
Exactly. You often have a coordinator agent that assigns tasks, maybe redistributes them based on how things are going. OpenManus and OWL are good examples, sometimes using hierarchical structures like a planner agent and separate tool calling agents. Some systems, like Alita, even have this self-evolution thing where they can monitor the task and actually provision or configure new specialized agent servers at runtime if needed.
Wow. Building its own team on the fly.
Sort of, yeah. These multi-agent systems are fantastic for handling highly complex parallelizable tasks. They offer a lot of flexibility and scalability. The main challenge, of course, is the coordination, making sure all those independent agents work together effectively.
Okay, so whether it's one agent or many, they're potentially dealing with just vast amounts of information, right? Retrieving tons of documents, intermediate results. How do they handle all that, especially when it likely exceeds what even a big LLM can hold in its immediate working memory, that context window?
That's where memory mechanisms become absolutely vital. They allow these DR agents to persistently capture information, organize it, and recall relevant bits across multiple steps, multiple retrieval rounds. This really helps reduce redundant work, like asking the same question twice, and improves the overall coherence of the final report.
So how do they manage the sheer scale? Millions of tokens, potentially.
Right, for those really extended contexts, DR systems generally employ three main strategies. The first, and maybe the most intuitive, is simply expanding the context window length of the underlying LLM itself.
Making the short-term memory bigger.
Exactly. Google's Gemini model, for instance, supports up to 1 million tokens now, which is huge. And they often supplement this with RAG techniques to pull in even more relevant info on demand.
What's the catch?
The main drawback is just the computational cost. Processing millions of tokens is very, very resource intensive. The second strategy involves compressing intermediate steps.
Summarizing as it goes.
Pretty much. The agent intelligently summarizes its own reasoning steps or the information it's gathered, reducing the total number of tokens that the main model needs to process at any one time. This significantly improves efficiency.
But you risk losing details.
That's the potential downside, yes. There's always a risk of losing some nuance or specific details during compression, which could theoretically impact the precision of later reasoning. It's a trade-off. And finally, the third main strategy is utilizing external structured storage.
Like saving things to disk.
Essentially, yes, but often in more sophisticated ways. This involves storing massive amounts of historical information, intermediate results, retrieved documents, etc., outside the LLM's immediate context window. This allows for persistent memory and highly efficient access when needed.
What kind of storage?
It varies. Some frameworks like Manus and OWL might use external file systems. Others, like WebThinker and AutoAgent, leverage vector databases. These are great for quickly finding semantically similar information, and some are even more structured. There's work using knowledge graphs to store information relationally, or systems like Agent Airsiv that simulate an academic repository where agents can share and retrieve structured outputs from previous tasks.
More complex, I guess.
These more semantically structured approaches offer potentially superior retrieval based on meaning, but yes, they definitely come with higher development and maintenance overhead.
Okay, so we've built these agents, given them reasoning, tools, memory, but how do we make them smarter? How do they improve over time, beyond just giving them better initial prompts?
That's a crucial point, because relying only on prompt engineering, just writing clever prompts, often hits a wall. You bump up against the inherent generalization limits of the LLMs, especially for really complex multi-step research tasks.
So we need something more.
Exactly. We need ways to actually tune the models. And we primarily see two main approaches here. First is supervised fine-tuning, or FFT.
Training the model on specific examples.
Right. SFT systematically optimizes the LLM for critical parts of the DR process. Things like formulating really precise search queries, generating well-structured reports, or learning how to use external tools more effectively. Systems like OpenRAG use adversarial training techniques within SFT, and AutoRAG focuses on autonomously iterating retrieval strategies during tuning.
What's the limitation of SFT?
Generally, SFT methods are trained offline. You create your data set, you fine-tune the model, and then you deploy it. It's usually based on static retrieval pipelines used during training. It's not continuously learning from live interactions. So the second paradigm, which is much more adaptive, is reinforcement learning, or RL-based optimization.
Learning from trial and error.
Sort of, yes.
Right.
RL offers a dynamic solution, particularly for things like online query generation and tool invocation. Think of it like the agent learning from real-time feedback. It performs an action, gets a reward or penalty based on how helpful that action was, and adjusts its strategy accordingly.
So it learns what works best in real situations.
Exactly. This significantly strengthens its ability to do that iterative information retrieval we talked about, to dynamically invoke tools when needed, and to integrate complex reasoning steps effectively.
Any examples?
Sure. Agent R1 is noted for integrating RL directly into its end-to-end training process. WebThinker uses a specific technique called iterative online direct reference optimization to improve its online performance based on feedback. And newer RL policy optimization methods like GRPO are showing advantages over older ones like PPO, helping agents learn faster and explore solutions more effectively. It's like having a better coaching strategy for the AI.
That's a fascinating leap. But okay, here's where my mind really goes. Can these agents truly learn and evolve entirely on their own, without us having to constantly retrain or update their huge internal models?
Ah, the dream of self-evolution. And yes, that's the exciting promise of something called non-parametric continual learning.
Non-parametric.
Meaning it doesn't primarily rely on changing the millions or billions of internal parameters or weights inside the LLM. Instead, it's a highly scalable alternative. Agents refine their capabilities at runtime by optimizing things external to the core model, their external memory, their workflows, their tool configurations, all through continuous interaction with the environment.
So they learn by adjusting how they use their resources.
Precisely. This allows for incredibly efficient online adaptation, often with minimal new data, and much lower computational costs compared to full retraining. It's ideal for these complex DR agents operating in dynamic environments. A really mainstream method within this paradigm right now is case-based reasoning, or CBR.
Case-based reasoning, like learning from past cases.
Exactly like that. Think of an experienced human researcher who builds up a mental library of successful past projects or solutions. CBR allows the AI agent to do something similar. It builds an external case bank of structured problem-solving trajectories, basically, records of what worked before on similar tasks.
And it reuses them.
It dynamically retrieves relevant past cases, adapts them to the current situation, and reuses the successful strategies. Crucially, unlike static ARG, which just fetches documents, CBR enables online contextual adaptation and really effective task-level generalization from a past experience.
Where is this being used?
We see examples like DS Agent applying it to data science workflows, LAM using it for generating functional software tests, and Agent ORS, which simulates that online archive-like platform where agents can share and retrieve prior research outputs, effectively learning from each other's experiences. And this self-evolution isn't just about memory, it can also come from dynamic infrastructure adaptation. We mentioned Alita earlier.
The one that provisions new servers.
Right. It monitors the task requirements and can literally provision and configure new specialized servers or tools at runtime based on environmental signals or task needs. It seamlessly extends its own capabilities on demand.
Wow, so this opens up truly incredible possibilities, doesn't it, for genuinely autonomous AI research assistants that are continuously improving themselves.
It really does. Imagine the potential impact on the sheer pace of discovery and innovation.
That's a truly profound thought. Okay, we've dug deep into the mechanics and the learning, but who's actually building these things? Who's deploying these incredible systems out there in the real world right now?
Well, as you might expect, the major players are heavily invested. OpenAI Deep Research, for instance, is out there. It seems to employ a single-agent architecture, likely with a heavily fine-tuned, learning-optimized model. It's characterized by that dynamically adaptive, iterative research workflow we discussed, enhanced memory for long context, pretty robust multimodal processing, and a comprehensive tool chain web browsing, programming tools for generating structured reports, and so on. Then you have Google DeepMind's Gemini Deep Research. This is built on their powerful multimodal Gemini models, like the 2.0 Flash Thinking model.
What makes it stand out?
A few things. It features interactive research planning. Remember the unified intent planning? Users can review and modify the plan. It uses asynchronous task management for better efficiency. It boasts those large-scale context windows combined with array ensembles for synthesizing multimodal data. And it's known for incredibly high-speed adaptive retrieval. Perplexity Deep Research is another significant one. They demonstrate really advanced capability in breaking down complex queries, running iterative web searches, and synthesizing those structured reports.
Their specialty.
A key strength seems to be the iterative information retrieval, combined with dynamic, prompt-guided model selection. They use a hybrid architecture that can intelligently switch between different AI models depending on the subtask, which is quite clever. Grok Deep Search from xAI is also making waves. It combines real-time information retrieval with multimodal reasoning. It features a pretty sophisticated processing pipeline that works at the segment level and includes robust credibility assessment and cross-source verification, sometimes going, reportedly, up to 7 layers deep to check facts, plus dynamic resource allocation and a secure sandbox for running code or verification steps. Microsoft isn't sitting still either. They've introduced 2 innovative agents within the Microsoft 365 Copilot ecosystem, Copilot Researcher and Analyst.
Integrated into Office tools.
Exactly. They can securely access your work data and web information. Researcher is designed for those complex multi-step tasks, like crafting a market entry strategy, pulling together internal and external data. Analyst uses OpenAI's models to transform raw data into actionable insights, focusing on transparency with a step-by-step reasoning approach. And we should also mention Alibaba Quinn's Quinn Deep Research. This leverages their powerful Quinn large language models. It focuses on dynamic research blueprinting, allowing for that interactive plan refinement and concurrent task orchestration to speed things up.
So it's not just one or two players, it's really becoming widespread.
Absolutely. What this really robust landscape tells us is that these solutions are rapidly proliferating, not just from the giant tech corporations, but also from innovative startups entering the space. It clearly underscores the technological attractiveness and, frankly, the substantial market potential here. We're seeing a significant shift towards these DR systems becoming foundational pillars for the next generation of intelligent collaborative research platforms.
Okay, we've seen the incredible power and potential, but let's be realistic. What are the big hurdles still remaining? What are the challenges we need to overcome? And where does the research go from here to push these boundaries even further?
You're right, there are definitely challenges. The two big overarching ones that keep coming up in the research are, first, the limited breadth and depth of information that these agents can actually access, and second, limitations in the efficiency and robustness of their execution workflows, how they actually do the work. So looking ahead, one absolutely key direction is to broaden information sources. Right now, they're mostly limited to publicly available web content or specific connected databases.
They need access to more specialized stuff.
Exactly. Things like proprietary interfaces. Imagine accessing a Bloomberg terminal for financial data or specialized scientific databases that aren't easily indexable. This requires developing what people are starting to call AI-native browsers.
Browsers built for AIs.
Kind of. Think BrowserBase or Perplexity's Comet project. These are being designed from the ground up for programmatic control by AI agents. They offer stable views of web pages, DOMs, explicit API hooks for interaction, asynchronous execution so the AI isn't just waiting around, and better parallel tab handling. The goal is to overcome the bottlenecks we see when trying to automate conventional browsers. Another critical area, maybe the most critical, is ensuring trustworthiness through advanced fact-checking. Hallucinations are still a concern.
How do we make sure the research is accurate?
Future efforts are focusing on integrating even more structured verification loops and self-reflection capabilities into the agents themselves. We mentioned Grok Deep Search doing multi-source cross-validation.
Up to 7 layers deep, yeah.
Right. And models like Zipu's rumination can actually pause their reasoning, check their intermediate conclusions against evidence, and then replan if they find conflicts. This isn't just about lowering factual errors, it's about the agent being able to explain why its conclusions are trustworthy. That's huge. Then there's boosting efficiency. Most current DR agents still plan and execute tasks somewhat linearly, one step after another.
Which can be slow for complex research.
Very slow. So future methods are looking at asynchronous parallel architectures. Imagine using structures like directed acyclic graphs or DAGs to represent the task, allowing for dynamic prioritization and running multiple subtasks simultaneously where possible. We might also see learned scheduling agents separate AIs trained, maybe using reinforcement learning, specifically to allocate subtasks efficiently and adjust the execution order based on real-time performance feedback.
Making the whole process faster and smarter.
Exactly. And related to that is smarter tool use, sometimes called tool-integrated reasoning, TIR. This isn't just about the agent calling a tool, it's about complex, multi-step reasoning with dynamic tool integration.
Understanding the tool's output and deciding the next step.
Precisely. And reasoning about which tool to use when, possibly composing multiple tools. Advanced RL frameworks with really carefully designed reward structures seem promising here. They can significantly enhance the model's ability to reason about tools and, crucially, generalize to using new, unseen tools they weren't explicitly trained on. A more meta-level challenge is what's termed benchmark misalignment, how we evaluate these agents.
The tests aren't quite right.
Often, yeah. Many public evaluations still rely on traditional question-answering datasets. The problem is, super powerful DR agents might just answer these from their vast internal knowledge, their parametric memory, without actually performing real-time retrieval or reasoning.
So the benchmark doesn't test what it's supposed to.
Exactly. There's an urgent need for benchmarks designed for the open web, using time-sensitive questions that can't be answered from static training data. Things like the BrowseConf benchmark try to filter out these parametrically solvable questions. We need continually refreshed leaderboards that genuinely assess real-time retrieval, reasoning, and tool use on the live internet. And critically, we need comprehensive benchmarks that evaluate the entire process, including the quality of the final generated report, the long-form narrative, the integrated tables and figures, the multimodal coherence. For those multi-agent systems, refining collaboration is key. Current optimization is tricky. Future directions might involve more sophisticated techniques like hierarchical reinforcement learning, HRL, which allows for layered internal rewards to encourage cooperation, or maybe dedicated RL-based scheduling agents to dynamically allocate tasks among the specialized agents more effectively. And finally, looking way out, that next frontier, self-evolving language model agents, expanding beyond the current case-based reasoning.
Even more advanced self-learning.
Yeah. Developing truly comprehensive CBR frameworks with maybe hierarchical experience traces, more advanced retrieval mechanisms for finding relevant past solutions, and enabling autonomous workflow evolution. Imagine the agent's workflow itself being represented as a mutable structure, like a tree or a graph, that the agent can dynamically refine and optimize using evolutionary algorithms as it learns and adapts over time.
Wow, what an incredible journey through the world of deep research agents. We've really covered a lot of ground from their core definition, how their advanced reasoning and adaptive retrieval works.
The communication protocols, MCP and A2A.
Right, how they see and interact with the web using APIs and browsers, the powerful toolkits they have,
Code interpreters, data analytics, multimodal tools.
and how they orchestrate it all through static or dynamic workflows, different planning strategies, those sophisticated memory systems.
Single versus multi-agent too.
Yeah. And finally, how they're being fine-tuned, optimized with RL, and even starting down that path of non-parametric continual learning, potentially evolving on their own.
It's been a fascinating deep dive, and it really highlights the truly significant potential here. These DR agents are really poised to transform complex research workflows, dramatically enhance human productivity, and honestly drive innovation across pretty much every academic and industrial domain you can think of. It's a genuinely exciting time to be watching this space develop.
Absolutely. So let's leave you with this thought. Imagine a world where your most challenging, your most time-consuming research questions are seamlessly handled by an AI assistant, one that's deeply informed, constantly learning, always evolving. Imagine being freed up to focus purely on the creative insights, the strategic thinking, the uniquely human parts of discovery. What new breakthroughs, what new insights, maybe even what entire new fields of discovery will this enable for you?